is just 1" by 1". We had this machined down at RMC Engineering in Gilroy. It's just there's 4 equal length bars, 14 inches, and then you have two end screws on both sides that are going to attach it. So you'll see that this side is going to be a little bit longer, just to kind of make up for the room for these rods to go in. How this moves is going to be on top of these guiding rods. So these things, 2 on each side, parallel, and then they move on linear bearings. As you can see right down here, they're attached using these clamps, and then the clamps themselves are going to be attached to sheet metal through this 3D printed ABS plastic, and then reinforced on top with sheet metal again. So everything you see here is going to be 3D printed, or everything you see blue here is going to be 3D printed. I mean, anything from with the brackets, we have these platforms, and then even on this center part right here, we have the servo. The servo moves on linear bearings, just like the rest of it on these parallel rods. But instead of using the clamps, this is just directly 3D printed around it, and you have once again this sheet metal reinforcing it. When we go over to this side, we're going to have this timing belt that's going to drive just the primary axis here, and it's done with the stepper motor. Just some more brackets here. Timing belt was a little bit tricky. You can see right here, we had to put that together ourselves. And once we did that, there was still a little tension, or not enough tension in the line, so the gears were slipping. So we came up with, I don't know if you can see, right here we have spring tensioner. How it works is, underneath we have a wing nut. So you tighten down the wing nut, which is going to compress this spring all the way. Once you do that, you slide this belt over the top. So it's going to be fairly tight, and then you just unloosen the wing nut up until you can see right here, this thing, it's not going anywhere. For the belt on the secondary axis, we have another tensioner. This is just a timing belt, spring tensioner. You can buy them online. This one, we took a torsional spring, bent that one around. So inside here is going to be the servo. This is going to be controlling the action of the pen. So right now it's up. If we want to put it down, we have it hooked up just to a button, and then you can kind of make your own designs. The pen is just clamped onto the side, so it's on this hinge arm. In the back here, I don't know if you can see it very well, but we have the let's see. So in the back here we have this 3D printed part. I don't know if I have another part here, but back in here, the belt's going to be clamped onto it. There's actually printed into the side of it is going to be where these teeth marks, just opposite, so it matches it. It's not going to slide anywhere. Right here is going to be a really interesting part. This is going to be just an outside pinion gear, and it's 3D printed. I don't know if we can pull this out, but inside we have just ball bearings that we press fitted, and then this outside design fits perfectly onto the timing belt, which just allows it to give a smooth motion. As you can see, just in some of the drawings that we've done, it's pretty smooth lines. So, this back in real quick. For a couple of these 3D parts, they're also a little bit more complicated than you guessed. Kind of like this pinion gear that I just showed you. Pretty much covered it.
We have a simple metal plate for the drawing area underneath the rig. It's being held by these 2 metal blocks to keep the paper from slipping. So, for the electrical components of the project, we started using these L298 drivers. These are the same ones that we used in the stepper motor lab. At the beginning of the project, we tried to use these stepper and motor shields coming from OSEP. We ended up burning additional pin inputs so that we can add any kind of sensors, any kind of buttons, whatever additional possibilities, and the storage for the code is 10 times larger than the traditional Arduino Uno. The entire rig has multiple control options. The sensor we incorporated is this 2-axis joystick, and this is for a live user control mode. So we have the code up below real quick. We'll demonstrate how the 2 axes on the plotter can be controlled by this 2-axis joystick. And the pen control is simply done by this push button here. We wanted to have multiple control modes, and using a simple analog device like this allows us to easily add additional ways to control this plotter in the future. We have a 2D touchscreen interface that can easily be used to control this using a finger. You can use any kind of combination of buttons or potentiometers, and it's all very simple changes in the code. Right here we'll demonstrate the Arduino automatically controlling this rig. It's a second method of control. And here we don't have to have any type of user input. The Arduino can fully run any sort of shape or user programmed run. So this is a simple spiral square sketch. It takes 3 lines and increments the size of each square around by 5 steps.
It's pretty accurate though.
Our third method of control is the combination of Arduino programmed control as well as user input. This is the timer. So aerial position. Let's give it some room. And what this mode does is it takes serial data from the Arduino IDE, and based on any alphanumeric character you input through serial, it prints it out. So we'll have C. Now, one of the biggest challenges we ran into for this project is uneven printing surfaces. So if there's any kind of tilt for the device, it can cause the pen to either press too hard or not hard enough. And that's something that we would definitely want to try and solve on any future revisions of this project. But for now, it can simply be changed in the code to set the pen at any specific height on the motor mount. So one simple variable change and any sort of movement of the machine takes just one quick calibration, and you can get it as close to perfect as possible.
Yeah, that just has to do with these rods down here. They're not perfectly chrome rods, or they can be polished up just a little bit. So that's another future work that we'll be doing.
And one final future revision we'd like to do is integrating our original stepper motors we purchased. These wound up being too high of an amperage requirement for any of our drivers to handle, so we were able to find some lower amp stepper motors, but we have more powerful drivers here with these higher amperage stepper motors that could be integrated, and all the 3D printed parts fit both of these motors, so it would be a quick fix after these get wired and programmed into the software.
Yeah, these motors were actually taken from the 106 lab. I believe they're also NEMA 17s, but they had an encoder on the back. You can kind of see over here. It's going to be just this rod. There was also a magnet on top, which we bit smaller than the other design. You can kind of see where we just used a foam to secure it into place. Same thing with this. You can kind of see under there, same deal. I think one more thing I just wanted to add to the design was just a lot of these 3D printed parts were integrated with different screw holes, different. This one right here in particular has a. Let's see if we can get this. Doesn't want to come out. Yeah, so this one right here, you can kind of see directly down in there. That's a sheet metal plate on top of a 3D printed part, and then a sheet metal plate on bottom. Both of these sheet metal plates are fit to the bearing size. And then also on this 3D printed part we have just kind of a circular imprint that matches the racer, or the outside diameter of the racer, and so it's kind of press fit into there. And a lot of these parts, that's how they were machined. So like I said, this one right here is we're very excited to see that work. And then the same thing over here. This is actually, you have sheet metal on the bottom that's attached directly to the aluminum, which is then attached to the 3D print. And then in the 3D print, there are slots on the side where you took the sheet metal, and there, yeah. So you could insert that into there. And then if you look right here on the side, there's that screw hole. And the screw hole goes through the 3D print and both things of sheet metal. You have this back right here to keep it from coming up, so structurally sound. Like I said, there's a lot of tension on here, so it's been able to do pretty well.
And one additional thing about the software features is for the typewriter mode, we've implemented a font size. So here in the red, we have the base font, and here in the green is double that. The software supports up to 3 times this base font here, so you can change the size of what you want to print. As well, the typewriter software can implement new line features, so it can keep track of how many letters are on each line, and when you send the new line character through serial, it will be able to track back to the original position and bring it down to the next line. And all of these things are configurable in software, so anyone trying to reproduce this project can easily modify it to change any of the specifics for the software.
And then just a couple, that's one of the things where you just enter text into the serial monitor, have it print out. And then I guess maybe just a closer look at our circuits. This is just on a cork board, so for easy mobility, if we want to move the